So welcome back. This is the second lecture of COMP9418, and we are going to talk about propositional logic. Something that's interesting about propositional logic is that it's one of the simplest forms of logic. We are interested in defining events using sentences. And these events are going to be interesting for us in the future because as we study probability, we are also interested in events. So both formalisms work with events, with the difference that in logic, we only have true or false. And in probabilities, we can associate a degree of beliefs. So when we are working with logic, we are very confident about everything. But when we start to work with probabilities, we can associate some level of uncertainty. And this will allow us to think in the presence of uncertainty. That is one of the main objectives of artificial intelligence. So this lecture will provide an introduction to propositional logic. We will study the syntax and semantics of propositional logic. That means the syntax is how we write some valid sentences. So we are interested in building well-formed sentences that have an interpretation that will be given by the semantics. We will also touch the problem of monotonicity of the propositional logic, something that we have already seen in the previous lecture, but we go in a little bit more depth. This is going to be useful to us for the next lecture when we start in discussing probability calculus. When we start with probability calculus, we're going to change, but we're going to think as an extension of the concept that we saw in probability in propositional logic, because we will add some degrees of beliefs to the sentences. This will allow us to reason in the presence of uncertainty. So let's start with the syntax of propositional logic. So the syntax is how we write valid sentences. So we need a set of rules that will allow us to write the sentence that are valid in propositional logic and that have some meaning that we're going to see later when we discuss the semantics. But let's start with a simple example first, and we formalize these ideas later. Let's suppose that we have at home one alarm that can be triggered when we have a burglary, right? But this alarm has a problem. When we have an earthquake, the earthquake can also trigger the alarm. So we can start thinking about variables. And one variable will be alarm. The second variable, burglary. And the third variable will be earthquake. And we can start to put together those variables. And in order to put them together, we need some logical operators. One of them is disjunction. So we can think of one event that is composed of burglary and earthquake, and we say that this event will be true when or burglary or earthquake are true. So we use the logical disjunction for expressing this sentence, and it will be burglary or earthquake. Great. So now we can make it a little more complicated by adding a new operator that will be the logical implication. So we can think that this event, burglary or earthquake, can trigger the alarm. So we will say that burglary or earthquake imply an alarm. Okay, that's interesting. So we are basically saying that we need one of those events, or it can be both at the same time, in order to have the alarm being triggered. So the alarm will be true. But it means that if burglary is true or earthquake is true, then we can conclude the alarm is also true. It should be also the opposite, right? If the alarm is not true, it means that we didn't have a burglary or an earthquake. So a burglary and an earthquake. So we can write this too. We can say that if we didn't have a burglary and we didn't have an earthquake. So it will imply that we will not have the alarm trigger. So what we are doing here is composing, starting with very simple things. There are variables, and using those logical connectors to put the variables together in a very well-formed way, so it will have some meaning to us. Okay, let's see how we can make it in a little bit more formal way. So the syntax of propositional logic will be the following. So we start with variables. For simplicity, let's assume that our variables, the names are P1, P2, P3, and until Pn, right? Of course, when we're working with a real problem, we will avoid using those names because they having not a particular meaning, so for the person that is reading. But for now, it will keep things simple. These variables are called Boolean variables or binary variables because they can only assume two values, true or false. And when we have a sentence that says just the name of the variable, like P1, it means that this variable is true, right? So this is the simplest sentence possible in propositional logic. We call it an atomic sentence, and it has a meaning. It means that the variable P1 is true. Okay, now that we have this, we can start composing more complex sentences. And the rule is the following. Every propositional variable, Py, is a sentence. And also, if we have two sentences, alpha and beta, so we can create a new sentence that is composed of negation of alpha, alpha and beta, or and alpha or beta, right? So we can think of the following. If we have a P1, it's also valid to say not P1. It's a valid sentence, right? And if we call this alpha and we have some other beta that is like P2, we can compose those two things, writing, for instance, not P1 and P2, or in another example, not P1 or P2. So the first one, not P1 and P2, and the second one, not P1 or P2. So, and we can start doing more and more complex things, right? And making the sentence longer. So those rules that we defined, they just involve negation, conjunction, and disjunction. But we know that there are other operators, for instance, implication and equivalence. And shouldn't we in some way define the rules also including those operators? And that is possible, of course, and people like those operators because they make it the sentence easier to read. But we don't need it to, because those operators and any order that we might be interested, they can be defined as compositions of the three primitive operators. So we can use negation, conjunction, and disjunction to define other operators that we might be interested. So, for instance, we have this equivalence rule here that alpha then beta is equivalent to not alpha or beta, and we can show this, right, just by writing and taking note of all possible values. I'm going to use 1 for true and 0 for false. So I'm making here all the possible combinations of alpha and beta, and we can compute alpha implying in beta. So true implies in true is false, true implying false is false, false implying true is true, hard to believe, but it is true, and false implying in false is true, right? And we can compute the negation of alpha, simply inverting here 0, 0, 1, 1, and we can compute not alpha or beta. So we have here one column, and the other column that we are interested in going to be or. So 1 or 0 is going to be 1, 0 or 0 going to be 0, 1 and 1 going to be 1, 0 and 1 going to be 1. All right, 1. Right? So if we look at these two columns, all right, they are equal. It means that these two sentences, they are equivalent. All right, so we can do that also to the equivalence operator. We can show that alpha is equivalent to beta is equivalent to say that alpha implies in beta and beta implies in alpha, right? And you can do it by yourself and show that. All right, our final definition in this slide is saying that a propositional knowledge base is a set of propositional sentences. And you will take alpha 1, alpha 2, and alpha 3, and so on until alpha n. You're going to interpret that as a conjunction. So you're going to be alpha 1 and alpha 2, and so on until alpha n. Okay, great. So it's a good time for one example. So let's use a digital circuit, because digital circuits are very simple, and they are composed of logical gates. So it's easy to interpret them as propositional sentences. If you are not to these gates, this is the negation gate, right? This is a conjunction, an AND gate. This is an OR gate. All right. So if you have this circuit and you want to interpret this as a set of propositional sentences or as a propositional knowledge base, what we need to do is first assign values or create variables to the wires, so we can interpret when the wires go to 1 and to 0. So we're going to use this convention that we associate 1 to true and 0 to false. It's called the positive logical convention. And we're going to give names to the inputs, like A and B, and outputs, C. But we also need to give names to the internal wires. We call it X and Y. And it's important because we need to model the internal states of the circuit in order to compute the output. So what sentences can we have in our propositional knowledge base? So, well, we look at here and see that A goes into this negation gate and leads to X. So we can say that A will imply A not X. I'm going to write it slightly different here using the notation that we were using before, in not X. All right. But that is not all. We need to think what happens if we have not A, right? And if we have not A, will imply in having X. So not A will imply in X. There is these two signs in order to have a complete model. Let's look at the AND gate. So we have A and B will imply in Y. As you expect, if we have not A and B, this will imply in not Y. And for the OR gate, we have X or Y implying C. But we also have not X or Y implying in not C. I am forgetting to use the same notation in a constant way. All right. Great. All right. So we have our propositional knowledge base here for this circuit. And we can make some analysis if you want to, right? So what is going to be the output for the variable C when we see an input that is something like not A and B? Okay, we can see which rule is gonna fire. So we have not A, so we will have X. Great. Now let's look at here. We have not A and B. not A and B does not appear here. In order to activate Y, we need to have A and B, but we don't have both, right? If you look at here, what we have here is not A and B leading to not Y. So if we separated this and we say that it's going to be not A or not B, will imply in not Y. And we have not A here. So we have one side here. We don't need it both because it's an OR, so it will imply not Y. So we have also not Y. Now we have X and not Y. And this is going to go to the OR gate. Well, we have X. And if we have X, it will be sufficient to activate C, right? So we can find this rule here, this one, and we conclude that we have C. So the output will be high for C in this circuit if we have low for A and high for B. Great, so having seen how to make some sentences using propositional logic, so we haven't seen the rules that define well-formed sentences, so we can create them. Now we need to start to give some meaning to those sentences, and this is the part of the semantics. So the semantics is going to be important for us because it will allow us to define some important properties such as consistency and validity, but also the relationships such as implication, equivalence, and mutual exclusiveness. So let's come back to our example, the alarm, and think about one of the sentences that we wrote, that is burglary or earthquake, implying an alarm. If we accept this sentence, it is also true that we need to accept that burglary will imply an alarm. And we know that is true because this is an OR, right? So it is a disjunction between this, burglary and earthquake. So if burglary is true, the whole sentence here, the whole left side of the implication will be true, and it will lead to alarm being true too. So we can say that this is a logical implication of the first sentence. If we accept the first, we need to accept the second one. This is the process that we call deduction. So we can deduct some new sentence, some new knowledge from the previous one. Well, for very simple ones, we can do that by just looking and accept that. But there are some that are more complex. So this third sentence here is also an implication from the first. Alarm and not burglary will imply an earthquake. But it's a lot harder to figure out why this is true. So we needed some formal mechanism to make those derivations for us, right? And we can look at very simple ones and make it by hand, but this more formal mechanism will help us with the more complex one. So we can look at some simple ones like A and not A is inconsistent, right? So it means that it will never hold. Why that is true? Why that is happening? We can think of A. So A, again, A10, right? We can think of not A, 01, and we can think about A and not A. Well, and not A will be always 0. So there is no situation, there is no word, as we say, that holds A and not A. So it will never happen. We call it as inconsistency. We haven't seen inconsistency before. So in the previous lecture, we were discussing that some assumptions could lead to inconsistencies. And when we have an inconsistency, we had to remove the assumption, right? So what is going on is that when we have an incorrect assumption and that leads us to inconsistency, it means that our knowledge base will never be true for any possible combination of values. So we need to remove the inconsistency, otherwise we cannot reason about anything that we have in the knowledge base. At the same time, A or not A will be always valid. So if we look at A and not A and not A, will be always 1, always true, right? And we can think of something more complex, something like A and A implying B implies in B. What does it mean, right? Remember that if we have A with nothing together, nothing, no other operator here, it means that A is true. If A is true and A implies in B, so B must be true too. And we can have A or B equivalent to B and A, so we can switch the order. It's going to be the same thing. That's great. So these simple ones we can figure out by ourselves, but if you want to think about something more complex, we need to formalize this concept better. So we can think about some other problems, right? Some other sentences. For instance, we have A implying B is equivalent to not B implying in not A. Sorry, there is a typo in my slides. To think about that, we can think about one example, something like something like UNSW students. If you are a UNSW student, it implies that you are smart. Okay, something like all UNSW students are smart. But if we find someone that is not smart, so it's not smart, it will imply to us that that person is not a UNSW student, right? Because all UNSW students are smart. We can also think about something like this: A implying B and B imply and A implying not B will imply not A. Right? That must be true because A is implying at the same time in B and A is implying not B. If A is true, we will have an inconsistency because we will have B and not B at the same time, and we cannot have it. So the only possibility is that A is not true, A is false. So we will not trigger any of these two rules, and everything is okay, right? So we needed some more formal definitions of the logical properties, so we need to reason about that. So we started to think about the concept of words, right? The word is going to be all possible assignments that we can have to the variables, and we're going to look at all possible values of true or false that we can assign to the words. So we will continue with that in the next video. Let's take a break now, grab a coffee, stretch your legs, and see you soon.